we get started? We're going to continue with chapter 21. Are there any questions before we get started? Anyone? All right. It's third week already. We have a test next week. Hate that. I hate tests just as much as you do, by the way. Someday what I'm hoping for is that they have this thing, you walk up and you put it, it's a brain scanner. And it will just, you know, give you your grade. They'll know, see how much you have in your brain. And then we don't have to do tests, right? You'll still have to study though. I don't know. It's my dream. All right. Okay, so we're talking about the acetal mechanism last time, and I told you there was a very high likelihood that I would put the acetal mechanism on the test. Okay, so we went through the base catalyzed reaction, and with the base catalyzed reaction, you can't make an acetal with base. It stops at a hemiacetal. So something to keep in mind. So we stop right here at the hemiacetal. In the acid catalyzed reaction, generally can't stop it right here. So if you want to make a hemiacetal, you should use base. Generally not isolable, it will go all the way to the acetal. So we went through the base catalyzed mechanism to form the hemiacetal, and then we went through the acid catalyzed mechanism to form the hemiacetal. And here we are. We stopped at the hemiacetal, and then on the next page, we were continuing with acetal formation. All right, so there are two ways to do this. On both methods, you protonate the hydroxyl here because that's going to leave. And the way it turns out with these acid catalyzed mechanisms that we're going to be doing over the next several weeks, in an acid catalyzed mechanism, you always protonate the leaving group first. Okay, so here we're going to protonate first. And then the way I do it is I have the electrons on oxygen come down and kick off water, but you can certainly show it this way. It makes you draw one more thing here. This leaves. And then we can draw the resonance structure here. So these are two resonance structures for the same compound here. So let me just put brackets around there. And that is also fine. OK, and then we want to keep going, don't we? Because we're not done yet. So then methanol is going to come in and attack. So we're replacing a methoxy group with a hydroxy group, but we're not doing it by an SN2 reaction. So as you can see, we are one step away from a hemiacetal. What do we have to do? What's our last step? Our last step is to deprotonate. So I'm going to just deprotonate with methanol. So in an acid catalyzed mechanism, we're deprotonating, and then we're actually going to regenerate our catalyst. So it looks like that. Questions on the acetal mechanism? Anybody? Yes? I don't grade reversible arrows, so you don't need to worry about these guys. On the exam, I grade curvy arrows. So don't get worried about this part right here. I don't grade that. More questions? Anybody? All right, important points about acetal and hemiacetal formation. Hemiacetals cannot be converted into acetals with base. We mentioned that already. So there, we're making that point again. Use acid catalysis to go all the way to the acetal. Hemiacetals are difficult to isolate unless the hemiacetal is part of a 5 or a 6-membered ring. All right, so if you had something like this and you did an intramolecular reaction, you can actually isolate this compound. And hemiacetal is favored. So in this case, Hemiacetal is favored, so we don't have to drive the equilibrium. It wants to be in a 6-membered ring. So most of the time, the aldehyde or the ketone is favored, but in this case, the hemiacetal is favored. And the best example here, this is glucose as a hydroxyaldehyde. And only a very small percentage of glucose is in the what we call the open chain form. So it's the open chain form. It likes to be in a ring. And so long arrow to the right, short arrow to the left. And this is going to be, we're going to talk about this more in depth in the very last chapter in 51C. And you'll get really good at drawing these. So you thought you were done with drawing chairs? No. So notice all these hydroxyls are in the equatorial position. So that certainly makes it easier to remember the structure of glucose. Harder is to actually pick out the hemiacetal carbon. So remember, when we look for a hemiacetal, we want a carbon that's bonded to a hydroxyl and a methoxy. So right here, this carbon is only bonded to a hydroxy, so that's an alcohol. Likewise, that's an alcohol, that's an alcohol, that's an alcohol. This one right here, and I kind of drew that a little weird. It looks like there's, I got to fix that. This carbon right here is bonded to a hydroxyl and an OR. And so it's a hemiacetal. So that's our hemiacetal carbon. So let me go back and fix that. Kind of looks like I have an extra bond. Oh, now look at that. So now things are really going to be. Is that better? Yeah. And now let's label that hemiacetal carbon. So there's a question on sapling you might have already run across where they ask you to say which are hemiacetal, acetal. You know, by the way, there is a small issue here with the words hemiacetal and acetal. Some of our OChem textbooks use hemiacetal and acetal for everything. Other textbooks that we've used in the past use ketal if it's from a ketone and acetal if it's from an aldehyde. Okay, so there's a distinction there. And I learned it hemiketal, hemiacetal, ketal, acetal. But then, you know, the books that we've had over the years don't do the ketal anymore. But if you see that, that's what they're talking about. So we just use hemiacetal in this book for anything that has a carbon bonded to a hydroxyl and an OR group, whether it came from a ketone or an aldehyde. Okay, so there's just a little bit. You might run across hemiketal, and it's just the same thing. It just comes from a ketone. All right, so hemiacetal carbon. And so this is glucose in the hemiacetal form. And I think that at equilibrium, this is definitely greatly favored at equilibrium. I think there's like less than 1% in the open chain form. So this is greatly favored at equilibrium. So with these guys, where you have the acetal in a 6 or a 5-membered ring, you can stop at the hemiacetal with acid, okay, because that's what's favored. Questions on that point there? Anybody? Same factors that govern equilibrium in hydrate formation also govern equilibrium in hemiacetal and acetal formation, so you can go back and review that. The more stable the carbonyl, the less favorable the addition. And addition is favored for formaldehyde and aldehydes with electron withdrawing groups, just exactly like with hydrates. So we can follow the same principles. Reaction must generally be driven to completion using Le Chatelier's principles. And so, and to drive the equilibrium, you typically use a large excess of alcohol or remove water as it's being formed, or both. You can do both things. So there would be a large excess here. Let's draw the product. or OR prime. We've got two of them here. Our side product is water, which we want to pay attention to if we're trying to figure out how to drive equilibrium. So a large excess of water or remove water as a large excess of alcohol or remove water as it's being formed. So those are the two most common ways. The standard way to remove water as it's formed is to azeotrope with benzene or toluene. All right, so let me show you what the setup looks like for that. And this is using a Dean Stark trap. Kind of a really cool reaction. I did this reaction and I thought, oh, this is so cool. I'm actually synthesizing water in this reaction. So that's on the next page, and I'm going to show you what that looks like. So this is from a Brown and Foote book that we used to use. It's a really great drawing of this. I would love to do this in the undergraduate labs, but the Dean Stark traps are really expensive. All right, so here's the idea here. Here's your reaction. You have, let's just say aldehyde. What are they using? They're using aldehyde or ketone, and you're using alcohol. You got to have two alcohols because you're incorporating two alcohols in your product. And then you mix that with benzene or toluene. Why benzene or toluene? In this case, they're using benzene because benzene forms an azeotrope with water. So what's an azeotrope? It forms in the gas state, it forms a structure. The boiling point is different than benzene and different than water. It's at some intermediate value. So they actually they co-distill. So you're doing this reaction, you're boiling benzene. Benzene, as the water's formed, is forming an azeotrope. And so it comes up here, it comes up here, it comes up here, and then it goes into this condenser right here, right? So this condenser, once it condenses, the benzene and the water don't mix anymore, do they? They form a separate layer. So what happens is it comes down here, and it drips down in here. What's more dense, benzene or water? Water goes to the bottom. Okay, so as soon as this condenses, they're no longer together, and so the water goes to the bottom, the benzene goes to the top, and so once you get too much benzene here, if this overflows, it just drips benzene right back into the reaction. Okay, so that allows you to you can actually measure the amount of water you have here. The one that I used had gradations on here, so you could measure how much water am I actually forming in this reaction, and then you'll know when you're done here. And then if this gets too full of water, you don't want the water to go all the way up here, or else it'll go back in here. You can just drain it with the stopcock. So this is how the very common way to drive water off as it's formed. And that's a Dean Stark apparatus, or you can call it a Dean Stark trap. So really, really nice drawing of that. All right, so by the same token, if an acetal is placed in excess water with a trace of acid, the ketone will recover from the reaction mixture. This is known as a hydrolysis. So this is a reversible reaction. We have the reversible arrows right here. At equilibrium, the ketone is the thing that's favored. So without driving it, it's going to want to go back to the ketone. Okay, so once you put that acetal on, it comes off very easy. So this is what it looks like. So here's our acetal that we just made above. Reversible arrows here, H3O plus, H2O. And you really only need catalytic H3O plus. That's all you need. And it wants to go back to the ketone. Same mechanism, but reverse direction. You need to know the mechanism in both directions. Next week in discussion, we will do the reverse reaction. Okay, so know both mechanisms. And then, so this will be discussion week 4, is we'll do that. So you may want to try it on your own before next week and see if it matches what we talk about in discussion. All right, so some more points we want to make. Since acetals can be hydrolyzed under very mild conditions to regenerate the original carbonyl, they are often used as protecting groups for aldehydes and ketones. Okay, they make great protecting groups for aldehydes and ketones. Aldehydes and ketones only. So you can make an acetal from an aldehyde, you can make it from a ketone. You cannot make an acetal from an ester, an amide, an acid chloride, a carboxylic acid. This is only aldehydes and ketones. And more commonly, rather than making this type of acetal, is to make a cyclic acetal when you're using this as a protecting group. So this one's the most common. And this would be the conditions, tosic acid. You could also use catalytic sulfuric acid, but more commonly tosic acid. So very similar to sulfuric acid. So that's what tosic acid is. Toluene, Dean-Stark apparatus. Why toluene? Toluene is more common than benzene now because benzene is a pretty bad carcinogen. So we try to avoid it if we can. And this would look like this. And we'll look at the mechanism for this reaction in discussion also next week. So that's a cyclic acetal. Side product is water. So we would drive this the exact same way using that Dean-Stark trap. Questions? Anybody on acetal formation? All right, so a little bit more about acetals. The reason why a cyclic acetal is used more commonly as a protecting group is for 2 reasons. Number 1, recall this formula from GChem. Delta G equals delta H minus T delta S. And mostly we have been ignoring, we've been assuming if delta G is favorable, then delta H is favorable. But we've been mostly ignoring this entropy component. But the entropy component can play a role in some reactions. We've just been pretty much ignoring it. It's been off our radar. So this reaction is, when you make a cyclic acetal, it's more favored because if you think about it, we have 3 reagents here. And if you look at the products, two products. So we're decreasing entropy here. So decrease in entropy is not good. Decrease in entropy disfavors reaction. And if we make a cyclic acetal, we have 2 reagents here. And we get 2 reagents in our product. So not as bad change here. So similar entropy. So that's reason number 1. Reason number 2 is that intramolecular reactions are more probable. So if you go through the mechanism to make the cyclic acetal, which we will do in discussion in the forward and reverse direction, you're going to get an intermediate that looks like this. And then you're going to have the alcohol attack here. Okay, so that would be intramolecular. And remember, making a 5 or 6 membered ring is very favored. This is going to make a 5-membered ring. And if you compare that to making a non-cyclic acetal, This is what it would look like. If you go through the mechanism, you're going to get the alcohol attacking like this. This would be intermolecular. So in the intermolecular reaction, you have to wait for those two species to collide. You have to wait till they collide with enough energy, and you have to wait till they collide in the right orientation. If it's intramolecular, you don't have to wait for the two species to collide. It's a much faster reaction, much more probable reaction. And remember, this is an uphill reaction. We are forming a product that's less stable than our reactant. So this is more probable. All right, so for all those reasons, that's the typical protecting group that we're going to use for aldehydes and ketones. Any questions on acetals? So that's our second reaction. We did hydrates first, we did acetal second, and now we're going to have addition of cyanide. So cyanide ion adds to the carbonate group of an aldehyde or ketone to form a tetrahedral intermediate called a cyanohydrin. So yet another new functional group for you. So here's what it would look like. Cyanide ion in step 1. This is a good nucleophile. Attacks carbonyl directly. And then once it attacks the carbonyl, what do we get? We get a deprotonated cyanohydrin, so we have a negative charge on oxygen. We've just formed a new carbon-carbon bond, so this reaction needs to go on your carbon-carbon bond forming page. And then in the second step, we add acid to protonate. So a cyanohydrin is a carbon that is attached to a hydroxyl and a cyano group, a cyanide group. So, and again, add this to your carbon-carbon bond forming page. This is a new carbon-carbon bond forming reaction. All right, so we make a couple points about this reaction on the next page. Aside from it being a new carbon-carbon bond forming strategy for aldehydes and most aliphatic, remember what aliphatic means? Not aromatic. Aliphatic means not aromatic. For aldehydes and most aliphatic ketones, the position of equilibrium favors cyanohydrin formation. So cyanohydrins are more favored than acetals or hydrates. For many aryl ketones, so that aryl means we're meaning right here that we have aromatic ketones. For many aryl ketones and sterically hindered aliphatic ketones, the position of equilibrium favors starting materials. So sterically hindered aliphatic ketone. Let's show an example here. Maybe a ketone with a terp-butyl group on one side and a methyl on the other, or maybe a terp-butyl group on both sides. So when you start getting steric hindrance there, you slow the reaction down quite a lot. All right, so here's an example, benzaldehyde cyanohydrin, also known as mandelinitrile. This is synthesized by millipedes. This is a reversible reaction. It's in our reversible reaction chapter. So it's synthesized by millipedes. It's also found in bitter almonds and peach pits. So if you have a bag of almonds and one of the almonds is bitter, you probably want to spit it out. because you're going to get a little bit of a cyanide if you don't. And peach pits. Okay. You also don't want to chew on peach pits, okay? So I had a student one time and they turned white as a ghost and they said, I chew on peach pits a lot. And I said, okay. And I'm like, you're here a lot, you're alive, you're fine, right? You haven't died. So you're fine. Anyway, so when threatened, it's released, okay? So millipedes release this when threatened. Inside the animal that this gets shot on, it undergoes enzyme catalyzed reverse cyanohydrin formation. Undergoes enzyme catalyzed. Reverse cyanohydrin formation. So it goes back to benzaldehyde, and the side product is hydrogen cyanide. Not enough hydrogen cyanide to kill an adult, but enough to kill a small mouse. So a little interesting fact about cyanohydrins. Questions on cyanohydrins? Anybody? Okay, we have another functional group we're going to talk about, and that is imines. And then we're going to talk about enamines. So a bunch of new functional groups in this chapter. So addition of primary amines to give imines. Imines are also known as shift bases. I didn't learn them as shift bases, so I don't call them shift bases. But I know when I went to grad school, and so this one guy was talking about, oh, shift bases. I'm like, what is he talking about? I had no idea until I looked it up. So it's just an interchangeable word for imines. And so here's what the product looks like. Something completely different than what we've been talking about. But we ran into these in the last chapter, didn't we? This is an imine. So it would be, it's like the nitrogen analog of a carbonyl. So instead of the oxygen, you have a nitrogen. So the nitrogen, of course, has 3 bonds because it's not oxygen, and but that's an imine. Side product here is water, and there's a couple different ways to do this reaction. You remove water like we talked about with an acetal, but sometimes you can precipitate the imine. So the reaction is driven by precipitation. If applicable, if you can do that, precipitation of the imine or a removal of water as it's formed. So this is another uphill reaction. The product is actually less stable than the reactant. Okay, so you will have to drive it if you want to get any decent amount of imine in this reaction. Followed compounds related to ammonia also react to form similar compounds. So you can, if you use a hydroxylamine, it forms something called an oxime. You don't need to know these names, but you may run across these. If you use hydrazine, it forms a hydrazone. If you use phenylhydrazine, it forms a phenylhydrazone. If you use 2,4-dinitrophenylhydrazine, it forms something with a short name, a short abbreviation. It forms 2,4-DNPH is the abbreviation. And so these are very, very similar. So very similar to an imine. So if you had, if you used hydroxylamine, okay, instead of this. In the place of the methyl, you'd have an OH right here, okay? If you use hydrazine in the place of the methyl, you just have another nitrogen. You just have another amine. So it's just like that. The mechanism is going to be exactly the same. So let's do the mechanism. All right. You're only going to have an acid catalyzed mechanism for this. We're not going to do a base catalyzed mechanism, and I'll show you why in just a minute. Acid catalyzed. pH 5 is the best. pH 5 is the best. So what happens is, so what that means is you're going to have, at pH 5, you're going to have some of the amine protonated, but not all of the amine protonated. Now, is nitrogen a good nucleophile? Yeah, it is, actually. So since it's a good nucleophile, it's going to attack directly. We are not going to protonate first, even though we have a slight amount of acid in here. We have a mildly acidic conditions. We're not going to protonate first because the nitrogens are really good nucleophile. Only a small amount of the amine is protonated, and we're not going to protonate the oxygen first. So good nucleophile. So this is really our exception here. Good nucleophile attacks carbonyl directly. All right. Again, reversible arrows. Let's see what happens when we do that. We have two things that we need to do here. We need to, nitrogen's going to have a positive charge. We need to deprotonate nitrogen, and we need to protonate oxygen. Could we do that intramolecularly? What do you think? Let's count atoms. You have to make a 5 or 6 member transition state. 1, 2, 3, 4. No, it can't reach. So we have to turn this into 2 steps. All right, so at pH 5, we have some protonated amine. I'm going to do this step first, but it's okay if you don't do this step first. Definitely, I'm going to do this step first. I'm going to deprotonate nitrogen. And then I'm going to use the protonated nitrogen to protonate oxygen in the next step. So in that last step, I just made protonated amine, and that's what I'm going to use for this. All right, so it's going to come and grab a hydrogen. We're going to break the nitrogen-hydrogen bond. This is what we call a carbanolamine. Another functional group, how about that? Carbanolamine, analogous to a hemiacetal. So carbanolamine, that's the first phase of the reaction. In the second phase of the reaction, we're going to do a dehydration. So we need to lose that hydroxyl group, and our rule of thumb for all these reactions is in an acid catalyzed reaction, we always protonate the leaving group before it leaves. So we're going to protonate that leaving group before it leaves. So I'm going to redraw the carbanolamine here. and I'm going to protonate oxygen. And this is the whole reason why we have acid in this reaction, slightly acidic conditions, is because we really want to protonate this leaving group before it leaves. All right, and then what's going to happen is the lone pairs of nitrogen are going to come down, and we're going to kick off our leaving group. So we've got a lot of mechanisms in this chapter, but they're very, very similar. Each one of them is very similar. And as you can see, once we do that, we're one step away. So this is an iminium ion, and now we just need to deprotonate to make the imine. So I'm just going to deprotonate with amine. And we're done. Oh, that's a positive charge, isn't it? Let's fix that. All right, so think you can do that on a test? Yeah? All right, so that's imine formation. Special points, the reaction. The reaction runs best when runs slightly acidic. I was going to draw a graph for you. I have it already drawn in here, but I didn't. So we're going to draw a graph right now. I just ran at a time during that non-break, that non-spring break that they like to call a break. Okay, so let's do rate of the reaction as a function of pH. So pH down here, we're going to have 1, 2, 3, 4, 5, 6, 7. Let's go to 8 and 9, okay? See what happens to this reaction as a function of pH. All right, so it starts off here. Really small rate of reaction. Right here, starts down right here. And then it peaks at somewhere, it's right around, we're going to say 5. It's probably closer to 4.5. And then it drops down to nothing at 8. So does that look centered at 5? Sort of. Hopefully yours looks better than mine. So this is about pH 4.5. You'll see it on some, it looks more like 5, and some looks like 5. And I just say 5 just to round it. All right, so let's look at this. Why would the reaction be 0 at a pH of 1? Essentially 0. Why do you think? So let's go back and look at the first step here. What has to happen in the first step? The amine has to attack the carbonyl. If that amine is completely protonated, can it attack the carbonyl? No. So that's why we have 0 rate of reaction. Okay, 0 rate of reaction. And so as we raise the pH, we have more and more amine that's not protonated, and the reaction can go quickly. Why does it drop down? What happens at 8? Why do we have 0 reaction at 8? If we're at pH 8, we're not protonating the hydroxyl when it leaves. Okay. Now maybe that doesn't mean a lot to you because we've seen hydroxyl leave before in certain instances. But in imine, we can have a hydroxyl leave when we're making a carbonyl, but an imine is not as stable as a carbonyl. So the reaction goes way down. So That's why we're doing an acid catalyzed mechanism, because that maximizes the rate of the reaction. So what you really need to write if you're making an imine on an exam is you write your amine and then you can just write pH 5 and I'll know exactly what you're talking about. Okay? So slightly acidic so that leaving group can leave. So we're going to label and we're going to say all the things I just said so you don't have to go back and look at the podcast to get that down. At a lower pH than 5, methylamine is significantly protonated. All right, so what it's going to look like is this. And that's no longer a nucleophile. We've just, when we protonate that, we change that amine into an electrophile. So no longer nucleophilic. No lone pair to attack with. And then our second thing is at high pHs, at higher pH than 5, the leaving group is not protonated. The leaving group is not protonated. It drops pretty rapidly here. And the hydroxide is not going to leave. The hydroxide can leave to form a carbonyl. We'll see that in chapter 21, but in chapter 22. But the hydroxide is not going to leave to form an imine. All right, so that's point number 1. Questions about that aspect of the reaction? Anybody? And the second point I want to make about this, in most of these acid catalyzed reactions, we've protonated oxygen first, and we don't here. So why is that? So in previous acid catalyzed reactions, we protonate the carbonyl first, and then we have the nucleophile attack. Okay, and so in this reaction that doesn't happen. We said because the amine is strong enough to deprotonate the carbonyl. I mean, the amine is strong enough to attack the carbonyl without protonation. But the other reason is that this is not formed because the amine will be deprotonated first. And the amine will be protonated first. Sorry about that. So methylamine is a stronger base than ketone. And that's not erasing very well. NH, the methylamine is a stronger base than ketone. In this case, acetone. All right, and if we were to make this protonated carbonyl and the amine came nearby, what would the amine do first? Would it attack the carbonyl or would it deprotonate the oxygen? It would deprotonate the oxygen. So in this is the one reaction, imine formation, enamine, where we don't protonate the carbonyl first. Questions on imine formation? Anybody? Yes?
Can you stop it as being
Not usually. So it's like hemiacetal. Yeah. Addition of secondary amines to give enamines. So yet one more. I think we're done with functional groups here after this. I think so. We'll see if there's something I'm forgetting. So the previous, to make an imine, you use a primary amine. This uses a secondary amine. So secondary amine gives enamine instead. All right, so let's draw the structure of an enamine. Double bond between two carbons now. Side product is water, so you can drive this the same way we did enamines. You can drive this the same way we did acetals. So very common to have this removed as it's formed. To drive the equilibrium. All right, so mechanism, the first step of the mechanism formation of the carbonylamine is exactly the same. So same as step 1 for imine formation. The second step is dehydration, and every step except for the very last one is also going to look like imine formation. So let's go through that in the last minute. We'll see how far we can get. So let's draw our carbonylamine that we get, and you'll see why this is different. We're going to protonate our carbonylamine. We're going to protonate oxygen so it can leave. You don't see any oxygen in an enamine, so we know that that group has to leave. So we're going to grab a proton from protonated. This is also pH 5, or catalytic acid. So far the same. This next step is the same. Electrons on nitrogen come down, kick off water. Only the very last step is different. Now, in the last step of imine formation, we deprotonated nitrogen. Can we deprotonate nitrogen here? No, there's no proton to deprotonate. So that's why this is different. So what we do instead is we eliminate what we call a beta hydrogen. So this is going to come in. We're going to grab this proton. We're going to move electrons over here and up onto nitrogen. And that's our enamine. So that's the difference here. If we had a proton to remove on nitrogen, we would have done it, but we didn't. So we're stuck with the enamine. All right, that's time. We'll stop right there, and we will continue this on Friday.